Question 2 is about creep. For a cylindrical S590 alloy, originally 10 mm in diameter, 500 mm long, what tensile load is necessary to produce a total elongation of 145 mm after 2000 hours at 730 degrees Celsius? Assume the sum of instantaneous and primary creep elongations are 8.6 mm. Now, creep is what we observe under high temperatures. So this is a type of deformation under high temperatures. Now we need to define what high temperature means here. We are above 40% of the melting temperature. So for the given alloy, the temperature is 730 degrees Celsius. Initial diameter is 10 millimeters. Initial length is 500 millimeters. And during creep deformations, creep processes, if you draw the strain versus time in the creep deformation, the creep strain epsilon is changing with time. The strain is not constant in time anymore. So this is instantaneous strain. Then we have a primary stage in creep. Then there is a linear steady state stage, and finally final tertiary stage here. So we can divide it into sections: primary, secondary, this is known as steady state, and finally tertiary, and this is rupture. Okay, so the strain rate here has a special name, steady state strain rate, and this is constant during the secondary stage of creep. So we have all our parameters, and the process lasts for 2000 hours. Okay, the primary and instantaneous elongations are already given as 8.6 millimeters. Total elongation is going to be 145 millimeters. Now, from here we can calculate the steady state elongation as delta L minus delta L instantaneous plus primary, and that is going to be 136.4 millimeters. Then we can calculate the steady state strain, which is delta L steady state over initial length L0, 136.4 millimeters divided by 500 millimeters, our original length. That gives us a strain of 0.2728. Then we can calculate the steady state strain rate as steady state strain divided by time. 0.2728 divided by 2000 hours. We obtain 1.364 times 10 to the power minus 4. Then we return to our chart here. At the x-axis, the steady state creep rate is given, and here stress levels are given for different temperatures. Now our temperature is 730 degrees Celsius. and this scale is in logarithmic scale, so for the steady state creep rate of 1.364 times 10 to the power minus 4, we need to take the log of it in base 10. The logarithm of base 10 of this number is minus 3.865. Then you go back here. So this is 10 to the power minus 3. This is 10 to the power minus 4. Minus 3.865 is somewhere here. Then from here you go to 730 degrees Celsius. I measured it before. This turns out to be around 200 megapascals. So at this steady state creep rate, the load on the material is going to be 200 megapascals, and the stress on it is going to be 200 megapascals, but the load is asked. So P over A, the load is sigma times A. We know sigma to be 200 megapascals, multiplied with cross-sectional area of pi d squared over 4. We know that d is 10 millimeters in diameter. From here you calculate the load as 15,707.96 newtons. That turns out to be 15.7 kilonewtons.